So yeah, guys, welcome back. This is day 6 of simple harmonic motion. And in the last class, I discussed a lot of things, a lot of different problems. And in the end, I asked you to think about the simple pendulum, right? So I am sure none of you have thought about it, but anyway, let me discuss that. So how do we look at the simple pendulum as an SHM? That is the first question. Because like first of all, it is not even going in a straight line. If you're talking about a simple pendulum and its oscillations, uh, it is not going in a straight line. And also, let us talk about a point where the body is at an angle theta, which is like extremely far away. And mg is acting like this. And if I can take the components, this will be mg sine theta, and this is mg cos theta. The tension and mg cos theta will balance each other, and the mg sin theta component is going to create the restoring force. That is what it is bringing the body back to its original position, trying to bring it to the mean position. Now, if you clearly look at it, the restoring force is not proportional to the displacement here. Clearly, the restoring force is not proportional to displacement. Now, we can solve this problem as an angular SHM. We will come up to that point later. Okay, there is a thing called angular SHM, where bodies are in SHM. It's not a single particle or a single body. It's like take this remote, you put it here and it oscillates. The whole body is oscillating. We call it as a compound pendulum. It's not a simple pendulum. It's called as a compound pendulum. We will get to that later. But looking at this thing for now, it is clearly not proportional to mg sine theta. The force, the restoring force is equals to mg sine theta. We're clearly not seeing anything like this, proportional to minus x or anything like that. So I cannot call this a simple harmonic motion. We cannot call the simple pendulum as a simple harmonic motion. So what you need to do is, what we do is, not just need to do, what we basically do is we consider a small oscillations which are like really extremely small. So small you can actually consider the angle as d theta, but let's just call it as theta only. It is so small, the oscillations almost look just on a straight line. And at this point, the restoring force is mg sine theta only. Yeah, it is still mg sine theta. F restoring equals to mg sine theta only. But it is so small, the angle is so small, I almost write it which is equals to mg theta. The force is so small, it's almost equal to theta. So force equals to ma, which is equals to mg theta. All right, cancel, a proportional to a is almost equals to theta, but we are still not done. Of course, if you want to put a minus, you can put a minus there because the force is restoring. Okay, now the important point is, you all remember L theta, the small length, if you call it as x equals to L theta, we can write this x equals to L theta. So from this, I'm going to write theta equals to x by L. So A equals to minus G into x by L. So if I clearly write it, minus G by L into x. Now we're getting A proportional to minus x, making this approximation. Taking this as an approximation, considering the angle is very small, now I'm getting the acceleration proportional to x. And this part right here, omega square, is becoming z by L. So omega equals to root G by L. So the time period becomes 2 pi by omega, which is equals to 2 pi by root over G by L, which will simply become 2 pi root over L by G. Now guys, please remember the point. When you're writing the time period, clearly observe that the time period is now depending on gravity. Remember the spring block problem? Remember the spring block problem where the time period was clearly not depending on anything else, but now the time period is clearly depending on gravity. So if you're talking about a simple pendulum, as long as you're talking about a simple pendulum, the gravity affects its time period. A spring block system, it wouldn't affect, but gravity clearly affects a simple pendulum. Okay, they even narrowed it down to another thing called seconds pendulum. They even narrowed it down to a thing called seconds pendulum. I'll tell you why. I allowed them, guys. Come on, who else do you want me to allow? I don't even know who, these people. Let them stay in the waiting room. I don't know. So seconds pendulum. Let's talk about seconds pendulum. So what a seconds pendulum is like, they take this length of the pendulum as 1 meter exactly. There is a theoretical idea in your textbook, in your IPE textbook. This is not really extremely important for JEE mains, but there are some problems about this topic. So that is why it is good that you go through the theory once in a while. A small simple pendulum, let's convert it into seconds pendulum. The reason why they call it as a seconds pendulum is they take this length exactly equals to 1 meter. So the time period becomes 2 pi root over L by G, which is nothing but 2 pi root over L is 1 meter. People sometimes write the value of G. G is 9.8, right? It is nearly equals to pi square. Nearly equals. So they put a pi square there. So what do you get is 2 pi into 1 by pi. So you get 2 seconds as a time period. You get the 2 seconds as time period. And this only happens, that is why you get a time period of 2 seconds. So every time the pendulum has to oscillate for a full oscillation, it has to exactly complete it in 2 seconds. They take this as a measurement, a unit of measurement in most of the cases, but this is not reliable. Okay, this is not reliable. This only works when the length is so perfect, when the length of the pendulum is so perfect, and the gravity, the value of gravity, acceleration due to gravity must be also should be equal to pi square. Otherwise, the time period won't be 2 seconds. Okay, if you're not fixed to that, if you're not fixed, they in fact do one thing. Do you know that? Let us talk about the time period. 2 pi root over L by G. They take L as 1 meter, and they find the time period. It is not 2 seconds. It could be 2.01 seconds. It could be 1.98 seconds. They finally find the time period, and from that value they actually find the gravitational acceleration due to gravity in any place. Do you know that this is an experiment in your +1 or +2 lab experiments? This is one of the experiments where they make you find the acceleration due to gravity in a place. Maybe you people have done it in the schools already, but what they make you do is they simply give you a pendulum. They give you a pendulum, at least the length of the pendulum is 1 meter. They clearly mention this point, that length of the pendulum, when I say length of the pendulum, the length in between this point and to the center of mass of the bob, the length in between. And here an important point, the time period doesn't depend on the mass of the bob this time. In the spring block system, it used to depend on mass. It doesn't depend on gravity. Here it doesn't depend on the mass. It only depends on gravity, right? So the center of mass, that length is 1 meter, and they make you oscillate it. They give you a stopwatch. They ask you to calculate the time period. uh, let's just talk about practical things here once, just for a minute. The thing is, when they ask you to calculate the time period, they don't let you just calculate it for one oscillation. It is difficult, right? Like, you switch it on and you switch it off in one oscillation. It is difficult, and the chances of error that you're getting is very high. So what they do is they ask you to take 20 oscillations, start the watch, let it have 20 oscillations, and then find the time period. So we already calculated, if it is for one oscillation, it is nearly 2 seconds. So if it is for 20 oscillations, it will be nearly 40 seconds, or 39.6 seconds, or 41.2 seconds. You might get any of these values for 20 oscillations, right? Since you're calculating it,
Yes,
oh, the screen has
virtually.
stopped. I'm sorry. I'm mirroring it again. Just a second. So the value can be anything, like taking this value for 20 seconds, so 20 oscillations, then calculate the time period, and from that time period, they make you put the time period in the formula that again that we have, t equals to 2 pi root over L by G. They make you find the time period practically. You can measure the length of the pendulum practically. From that, you find the value of acceleration due to gravity in any area. Aniket, what is it?
So the pendulum won't last till 20 oscillations, right, sir?
The kind of oscillations that you have is like very, very small. Okay, so they do last for 20 seconds, and also if it is properly done, it should be done in a vacuum chamber, in a small vacuum chamber. But in a vacuum chamber, you can't just put your hand and do all the stuff, right? So it's not that easy. But at least they ask you to do it in a room where there isn't a lot of wind and there isn't a lot of disturbance. Okay, and the
Okay,
oscillations are
sir.
very small, so it can actually last for 20 oscillations.
Sir, but friction and also will be there.
That is why you'll get a random values. So it is kind of acceptable. The value that you get is kind of acceptable only. Like the value, there will be errors, but it won't be that big.
Okay, sir.
Yeah, if you can calculate the friction also, that would be great. But can you calculate the viscous force that is acting on the pendulum and do the problem? The amount
No,
of
sir.
deviation that you get is like very, very small, so you don't have to worry about it. Okay,
Okay, sir.
that is just an experiment sake, that discussion, okay, that I just told you is the experiment sake. Let's talk about the kind of problems, all the theoretical problems, how we get. So they use this idea to compare the acceleration due to gravity. Like they give you a problem saying there is a pendulum on earth whose time period is 2 seconds, a seconds pendulum only. They call it as a seconds pendulum. Okay, they call it as a seconds pendulum if the time period is 2 seconds. They take you they take this into the onto the moon and they ask the time period. So what you need to do is once you have t equals to 2 pi root over L by G on Earth, now you have to write time period 2 pi root over equal into L by G on moon. As simple as that. As simple as that. They ask you problems like in a lift is accelerating upwards. What is the time period of a pendulum? So 2 pi root over L by G plus A. If it is accelerating downwards, it is G minus A. If it is if there is a car, let us say there is a problem in your HC Verma, I guess. There is a car which is accelerating sidewards. Why is it writing so thick? Oh, I'm sorry. So because of that, the pendulum is in that direction. So the effective gravity in this situation is like this. The gravity is definitely there, G, and then there is pseudo force A. So the effective gravity is like root over G square plus A square. So when you write the time period, you simply write the time period of the pendulum is 2 pi. It will simply oscillate about this point. The time period will be 2 pi root over L by root over G square plus A square. So whatever the case, whatever the problem that you're looking at, always try to write 2 pi root over L by G effective. That's all. 2 pi root over L by G effective, L by G effective, and that's it. That is how you solve the problem. Okay, G effective can be G plus A, G minus A, or G on the moon, the acceleration due to gravity on the moon, or acceleration. What happens when the a quick answer, raise your hand, everybody, if you know the answer. What is the time period of a pendulum in a satellite? What is the time period of a pendulum in a satellite? What is
Geostationary satellite, sir.
no any satellite? What is effective G in a satellite? Don't you know? Come on, Sharad.
Sir, zero.
Yeah, effective G effective was zero. We've already talked about it in a satellite, right? No, so because of that, the time period is not really defined. Like you don't even talk about simple
Pendulums.
pendulums oscillations in in a satellite. Okay, but strictly speaking, it still does have some time period. How do you say that? It still has a time period. If you move it, if you disturb it, if you give it an impulse, it still has a time period. What is that? Sharath, any idea?
No, sir. I'm
If you give it
thinking.
a velocity, it will simply go in a circular motion since there is no gravity. So the circular
Yes.
motion will have a time period, right? So technically speaking, the simple pendulum will have a time period even when there is no gravity, even the gravity is zero.
But it won't be the time period of an oscillation.
Exactly. There will be time period, but the time period for a circular motion, that's all. It's not a time period for a oscillation. Okay, G effective will be 0 in a satellite, so that is just another problem. Okay. In HC Verma, there is a problem. Let me discuss that anyway. There is a car which is making a turn. There is a car which is making a turn. So in this turn, there is a pendulum inside the car. What is the time period for this? We all know that the gravity will act downwards, and there is v square by r acting away, pseudo force, right? So when you write the time period of that, you simply write t equal to 2 pi root over. Anybody? Sharath, yeah, what will it be?
So we'll have to take the resultant.
Exactly, root over g square
Square
plus
plus
v
v
square by
square
r whole square. Okay, so this is how you find the time periods of simple pendulum in different cases. There are a lot of more cases for sure. I'm just not discussing them. If you can open the HC Verma, there are no problems in this page about simple pendulum, but there are
So
some
there is
problems.
there are
Look at this lady. I even made a meme about this lady. Like, look at the earring. Whichever somehow thought that he can make a question out of it. It's nothing but a pendulum, simple pendulum. He gives the length of the earring, and that's it, I guess. The length of the earring is as a time period of the earring, the way the frequency at which it oscillates. Okay, so that is one. And all these questions, look at this question: the pendulum of a clock. Look at 34, question number 34. The time period is given. How fast is it running? You're talking about if you have a 2 seconds pendulum, it will exactly run by time. All these questions are basically intuitive questions, like it's not related to the subject anymore. Okay, if it's a seconds pendulum, the time period must be 2 seconds. If the time period is 2.04 seconds, how fast will it run? Okay, think about these questions. And
there should be slow rate,
The
sir.
1 by 2.04 per second.
now the question Sharath is also making it, like whether it will be fast or whether it will be slow. If the time period is more, would the pendulum slow down or speed up?
It will be same, sir.
What? Let us say
So it'll slow down, sir. Like for the
you
same
have a
distance,
pendulum which is taking 2.04 seconds for its oscillation.
Yes, sir.
Then would you
So it
call
should
it,
slow down.
if you use it for 24 hours? If you use it for 24 hours, was it running fast or was it running slow?
So it was running with same
It is
time, right,
running
sir?
slow, sir.
The time period
It
is
is running
2.04
slow,
seconds.
sir.
How is it running at the same time?
it'll
Oh,
be
okay,
slower,
sir.
sir.
Time period has
Thing
changed. Sorry.
is, like since the
Like for the
time period is
same
2.04 seconds, you will wait for specific number of oscillations to happen. Let us say uh, for 1 hour to take place, like for 1 hour to pass, the pendulum has to oscillate for specific number of times. Okay, but to run the same number of oscillations, our pendulum, which is defective, will run for more time. So instead of showing the time right, it is showing the time less. You getting my point, right?
Yes,
yes,
sir.
sir. It'll be slower than usual
Yeah,
time.
so like how do I put it? Let us say I have a good watch and I have a defective pendulum. Okay, good watch and defective pendulum. The good watch runs 5 hours in 5 hours. It will show 5 hours in 5 hours. But this watch, it won't oscillate enough to show 5 hours because the time period is a little more. To complete one oscillation, it will take more time. To complete two oscillations, it will take more and more time. If come to complete three oscillations, it will take more and more time. So it won't complete the enough number of oscillations to enough number of oscillations that are good enough to complete that thing. So it will still show it as a slow watch. Okay, so all these questions, that question, and then looking at 35, 36. In 36 he's asking about what is the frequency on moon, so it's an easy one. And then the question, like the maximum tension in the string of an oscillating pendulum is double of the minimum tension. So where do you find the maximum tension and minimum tension in a pendulum? Anybody?
So maximum when it's going down at the least point.
Yeah, so this
Sir,
is the
at the
question from
mean.
vertical circular motion again. So they relate all the questions to this and ask different questions. Okay, Like when it is oscillating at the bottommost point,
Minimum at extreme, sir.
it will have mg and it will also have mv square by r. So that will be the tension. At extreme point, there is no velocity at all. So what you have is the tension here, T extreme, will only be mg cos theta. That's all. So what he's saying is at this point, the tension, uh, like this point, like at the middle point, T highest, let's call it as T highest. T highest is twice of the tension at extreme. So all you need to write is write this equation, write it equals to 2 into mg cos it, and you solve the problem. Okay. Vamshi has a doubt. Vamshi, what is it?
Sir, nothing, sir. I want to tell that answer.
Yeah. So now you get it, right?
Yes, sir.
Yeah. So if you look at like, look at 38, guys. It is exactly similar to a pendulum question, except instead of tension, there is normal force. So
There's
the
normal
body is
force.
clearly oscillating just like the way. Okay, let me show it here. So if you find a problem like in a curved surface, a body is trying to oscillate. When it is displaced by a some displacement, mg will act. It is mg sine theta which is bringing the body back. So we used to have tension in pendulum. Now we simply have normal force. That is the only difference. The oscillations are exactly the same. So to write the time period, you directly can write 2 pi root over L by G. But here, this is L. From that specific point, that must be the radius of that curved surface. So time period in this case on the problem must be 2 pi root over R by G in this problem. Okay. Now problem number 39, 40 and 39 is a rolling question. We will do that later. Rolling question is a bit interesting. You can do it. In fact, the body is in pure rolling. Let me discuss this question also. Like I'm
Sir,
discussing
many
all
people
this.
are in waiting room.
What?
Many people are in waiting room.
Let them be. I don't know any of them, man. I don't remember those names. So how can I let them? I'll again there will be disturbance. Let them be. I'll send the video again anyway. So they're not participating in the class. So what's the point of having them in the class? So in a pure rolling case, again, the body is not just sliding off, it is in pure rolling. So it is oscillating like this. I hope you can see my hand movement. It is oscillating
Yes,
like this. So which is an
yes,
interesting
sir.
thing. To solve this problem also, you can do, if you are brave enough, you can find the answer. Mg is like this. Mg sine theta acts like this, and then there is friction for sure. But all you have to do is write the restoring force. Here, restoring force is not just mg sine theta. The friction is also acting in the
MG
same
sin
direction.
theta
So you
minus
have to
F,
write
sir.
Mg sin
mg
theta
sine theta
minus F.
minus friction equals to mass into acceleration, and also friction into r equals to I alpha. From that, you have to find acceleration. Somehow manage it to bring it to proportional to x. Taking this angle as very small, okay? Taking that angle very small. I'm not giving you the entire answer. How to manage to
So
bring this?
sin theta will be theta.
I don't know. You people tell me. Okay. Somehow try to manage it to bring it to the point of saying acceleration proportional to minus x, and whatever the thing that lies here will be omega c. Okay. That is how interesting is this idea. Okay. There will be more problems like this, but as you move on, you will find. Again, the reason I'm all discussing all the models right here is there are maybe like 10 times more different models in SHM. So that is why I'm discussing these, so that you people can go and discuss solve the other problems. So look at 40, problem number 40. Pendulum of length 40 centimeters is not 1 meter. So it's not a simple pendulum. Sorry, seconds pendulum. For seconds pendulum, the length of the pendulum is 1 meter. I already mentioned that. So a simple pendulum of length 40 centimeters taken inside a deep mine. This is good. Deep mine. Like he's even given the depth. Do you remember again what happens here, guys? Tell me. You're going into the depth or going to a height. Do you remember these problems? And the gravity changes, Sharath?
Yes, sir.
Yes, sir. We have
Goes
to
to 2
change
pi
the
root over
gravitational
L
force
by G
accordingly, sir.
effective. In the
To
place of
that
G
G
effective, you
instead
either
of that
put 1
zero.
minus D by R or if it's going to a depth, if you're going to a height, do you remember this? G
Yes, sir. 1 minus 2h.
1 minus 2 h by r. Now please remember, you only use this when the height is
Really small compared to radius.
Really
Sir.
small.
exactly
Very,
when the
very
height is
small.
very small compared
We are
to the.
using binomial theorem, na sir here. That's why.
So guys, yeah, I think I've discussed enough models on simple pendulum. There are obviously more models, but all of them are linked to other topics. It's not really related to simple harmonic motion. So I am taking a step forward and skipping all the other problems of simple pendulum. You try to do them, you try to solve them, we will get there. Okay, if you have any doubts, we can definitely discuss. I want to discuss more different versions in simple harmonic motion. The one of the interesting questions to me in simple harmonic motion is this one. They take the planet Earth, dig a tunnel. Aditya, have a doubt?
Yes, sir. I wanted to ask, like, now we can start the DPP area, sir, in simple pendulum.
I didn't understand what you just said.
So should we start DPP in simple pendulum? He's asking.
Yeah, you should.
Okay, sir.
Yeah.
Thank you, sir.
So now in this problem, this is an interesting one. You take the planet Earth, dig a hole through the diameter, drop a body there. Drop a body there. What will happen to the body? It'll
Sir,
eventually
actually,
come out of the other side. Just a theoretical question. Please don't ask me if it is possible. Of course, it's not possible. What's your doubt? No,
oh, nothing, sir. I was about to answer it.
yeah. So it's not definitely possible, but the body simply will oscillate. That is the interesting part. You're talking about a theoretical ideal situation. The body will simply oscillate. Now, can we prove if it is an SHM or not? Aditya, can we prove?
Sir, we can prove it,
Let
but
us
how?
take a situation where it is at a distance x from the center.
No, sir, we can't prove.
Why?
We can, sir, because
We
No,
can
sir,
then
we can.
check.
Sorry, into D, right, sir?
Yeah. So at this point, let us say it is at a distance x. Let us try to write the gravitational force acting on it. The gravitational force acting on it. How much is the gravitational force?
sir,
You
G
remember?
GMM by R square
GMM by
into
R.
D.
Gm by r cube into d or x.
yes, sir. Here we'll take it, sir. Better.
You are talking about a solid sphere, inside a solid sphere. If you remember the value, inside a
Yes.
solid sphere, the gravitational field and the gravitational force must be written like this: gmm by r cube into r. If I hope you really remember this part. If you
Yes,
don't,
sir.
please go
Yes, sir.
back and to the topic
Yes,
of
sir.
gravitation and just revise that part.
Excuse me, sir.
Yeah,
Sir, if this thing we throw from a little height, then it will not be SHM, right, sir?
beautiful question. Yes, we will discuss that right after this. Yeah, if you throw it from a height, it won't be. So F equals to g m, wait a second, gmm by r minus, there must be a minus r cube into x. I write ma, so minus gmm by r cube into x, mass cancels out. The acceleration equals to minus gm by r cube into x. So gm by r cube will be simply,
Omega. So you zoomed in, sir.
yeah, I know. So omega square is equals to gm by r cube. So the time period will be 2 pi root over r cube by gm. This is the time period with which it oscillates along the tunnel of the earth. This is an interesting question. To make it a little more interesting, there are questions in your books. My question goes like this: if the tunnel is dug along this, like some random line, will that be an SHM or not?
It will, sir.
How are you so sure?
So because
No,
we'll
sir.
take the component and it will
No,
be
sir.
same thing again.
That
So
is
because
what you people need to
it
check.
will have the normal force along, sir.
Wait. This will be the mean position. It's not the center. This will be the mean position. Take a distance x from the mean position. Try to write the gravitational force towards the center. Try to take the gravitational force component. That component will be F restoring. Check whether the component, this red component F restoring, is proportional to x, this x. If it is proportional, yes, the oscillations along this line will also be SHM. If it is not, it is not. That is a homework for you people.
It is, sir. I already checked this one.
When did you check that?
Sir, once I saw this problem, that's why.
Oh, okay, fine, good. So, like Aniket is saying, he already checked, but for you people, you have to take some time and check whether it is an SHM or not. Now, let us skip that part. Let's skip the part of home. Sorry, this part, and discuss the question. Aniket, did you come across the question too? The other question that you just asked?
No, sir. This was purely doubt.
Yeah, there is a question where the tunnel is normally there, but the body is dropped from here. So what happens is it comes here, enters Earth, it actually appears on the other side, and then it comes back and it oscillates. It basically oscillates through the tunnel just like this. Okay, it will definitely oscillate through the tunnel just like that. But will that be an SHM? That is an interesting question.
No, sir.
No, so it will come to the center by oscillating like
Because
that.
if you're
So because
talking
head
about
square.
inside the sphere, yes, the force is gm by r cube into x. So force is proportional to x. That is good. But if I take a point which is outside, let us talk this as x. Let's talk about the force which is outside. The force is simply gm by x square. It is not proportional to x. This is just like a, oh, sorry, of course there must be an m. Gmm by x square. This is just basic rule of gravitation. The distance between the body you put here, and the center of the capital mass is x. So Gmm by x square. This is not proportional to x. So no, it cannot be an SHM. But yet there is a question where they ask you to find the time period in this thing also, in an advanced level model. Try to think about this one. This is an interesting one. Okay, they even asked you to find the time period even in this case. Okay, try to think about it. Try to give me some idea how you can solve this question. All right, now I'm moving on to the next question.
Yes, sir.
The next model would be, yeah, let's talk about the ring one. Do you remember that I've told you people that yes, this can also be proven as an SHM?
Yes, sir.
Yes, sir.
But we already do have an equation. Let us call this as x. Let us call this as r. Somebody remembers the value, the gravitational force value? Somebody remembers the gravitational force
GMM
The
value?
GM by root over d square
R
plus x square
Gmm by
Power
root
3 by 2.
over r
D square
square
plus
plus
x
x
square, sir.
square whole cube into x. Is this it?
Yes, sir.
Are you
Yes,
sure
sir.
about it?
Yes,
No,
sir.
sir, whole cube, sir. Sir,
No,
root over whole
it
cube.
should don't put the root, sir. Put it 3 by 2, sir.
It's the same thing,
It's
right?
the same thing, sir.
You
It's the same thing.
that idiot didn't
And
get
then
it. Let's just write it in
I'm
his,
using that, sir.
yeah, anyway. Now, of course, the force doesn't exactly look proportional to x. There are two terms of x. So then how did I call it an SHM back then? That's not a, decent way to do it. But if only this x is very, very small, if only x is very, very small compared to the radius, I can write this force. Let's look at it. GMM by, I take this r out as common. I get r cube 1 plus x square by r square whole power 3 by 2 into x. Do you understand what I just did there? I simply took the r out, like out of the equation. Now, if I clearly observe it, since x by r, x is very, very small compared to r, this value can be neglected. As in the idea of a binomial approximation, we can neglect this value and write f is nearly equals to gmm by r cube into x. From this point, you
Excuse me,
write,
sir.
yeah, of course.
So we have to multiply 3 by 2, right, sir, for that binomial?
But we do that for x by r. There is x square by r square, so they neglect it. That is why I even put
Okay,
a
sir.
nearly equal equation there. So this is nearly equal to an SHM, so they consider it as nearly equal to SHM, and they take this part and write the time period again, just like for the ring also.
Your constants won't affect the proportionality rate, sir. So whatever constant is there, it won't matter.
Yeah, that's why I'm not really considering about them. Like I I directly write the proportionality constant. I mean the proportionality equation there. You get it?
Yes,
Yes,
sir.
sir.
So even that is an SHM, interesting, quite interesting idea. So are there more? Not that I
So
can
that
think of
U
right
tubes
now.
are in that
What?
U-shaped tube with water.
Yes, sir.
Oh, right. Thanks for reminding about it. So we will discuss this problem later in fluid statics again. Anyway, when the liquid is supposed to be like this, when a liquid in a U tube supposed to be is like this, but somebody pushed it down and pushed it up by a small displacement x again. Okay, so what will happen? The new shape of the liquid, I'll draw a smaller diagram, don't worry here. So the new shape of the liquid will look like this. This level will be at a height 2x compared to the other level, because this went down by x, this went up by x. Now, the reason why it is trying to come back to its mean position is nothing but anybody.
The pressures there is in
Gravity,
order
sir.
to
Simply the
maintain
weight of this liquid
equilibrium.
is simply the weight of this liquid. Now, the weight of this liquid, if you try to write the weight of this liquid, F restoring is nothing but weight of that liquid. I can write mg directly. Now, m involves volume of that liquid into density of the liquid into g. Now, volume of the liquid involves the area of cross section into 2x into rho g. What do we have here? Can you people see? Force proportional to x.
X.
That is why that can also be
Okay,
an
sir.
SHM. What?
Okay, sir.
Yeah, that is why it can also be an SHM. That is the interesting part in it. Okay, so yeah, even this is an SHM, and
The bouncy ball.
Sir, bouncing ball.
Bouncing ball, sir.
a bouncing ball is definitely not an SHM. No, because there is no mean
Because the
position in the
restoring
first
force is
place.
always downward.
What? What?
The restoring force is always downwards in bouncing ball. So how can
There
you
is
say?
no such thing as, yeah, gravity is always acting downwards. That is one thing, and it's not really an oscillation. There is no mean position. It is coming and going back to the position. It's coming and going back to the position. It's not as if it is going into the earth and it's coming out. So even the restoring force is a constant force, which is gravity. There is no variable force there. So a bouncing ball cannot be an SHM. That is a question that we started, like we had it in the beginning, right?
Yes, sir. You told us to figure it out on our own.
Yeah, yeah. Now you get it now.
Yes, sir.
Yeah. So let me look at, oh, I'm sorry about it. Now you people can look at all the problems which are in this page. Try all these problems. Just give them a try. Like mostly about the pendulum and pendulum and pendulum and pendulum and just time periods and pendulum. Maybe at the end of these questions, like 48, 49, 50, 51, they are depending on rotational SHM, angular SHM, or compound pendulums, which I might discuss tomorrow or day after tomorrow. Okay, now that brings us, we have still have more time, so that brings us to back to these problems which we left behind. Now I would like to talk about all these problems. Okay, like each and every problem is different from other, so let's discuss all the problems one by one. I want to start with this silly one. 29. Go through this question. Can you please even tell me whether this is an SHM? It's as if the body, he simply says the body is oscillating like this. Can
Sir, it is
anybody
not an
even tell
SHM
me if
also.
No,
it's,
sir.
it's not even an SHM, but he simply asks a time period. That's all in this question. Simply asks you
He
to find the
told to
time.
neglect that bent effect also. That
Yeah, it shouldn't be like that. It should be smooth, otherwise it will just simply collide and things will turn
Stop.
ugly. So we don't want to do that. Sometimes you find these questions, kind of questions in HC Verma. I don't understand. I mean, there is a little, what do you say, uncertainty. Some of the problems are like really high standard. You have to take all the factors into consideration, and some problems you just have to neglect some things. Okay, he clearly mentioned neglect the small effect of bend near the bottom. So just don't do it. Just neglect it. Okay. So that is one question. It's not an SHM. We still consider it an SHM. Uh, Let me.
So like even if we don't consider the bend, sir, it won't be an exception, sir.
No, yeah. Even we don't consider. Even if we consider or don't consider, it's not an SHM. I'm just saying, like, it's not really the right way to put a problem. I just didn't like the way it is. Okay, like you can frame it better. That's what I felt. Okay,
It's a periodic motion and he's asking time period. Just
exactly. Yeah, it's just a simple periodic motion. It's asking the time period. Now look at the question number 28. They don't really fit anywhere. They're just random questions. They don't really fit into the style of teaching. Like, do we have to teach? Why don't I just leave it for you people? Why don't I just leave it for you people to figure out? Let me deal with some other good questions. Okay. Guys, look at this one, 31. Just take a look, not right now, maybe after the class, and in tomorrow's class I will show you why this is an SHM. Okay, this is quite an interesting one. This is quite an interesting one. This is an SHM, although the rotation of the wheels is given wrong. In my opinion, the rotation must be in the opposite direction, but this is an interesting one. The question number 31. Let's talk about the big questions, the good questions. Let's talk about 23. Can somebody tell me what will be the time period here? Try it by looking at it.
so we normal, sir, it will be like k of that normal formula.
So how
2
much?
pi
M by K, root over M.
upon k,
Simply
sir.
2 pi root over m by k. Yes, the time period is simply 2
He just
pi root.
changed the position. Just nothing else.
Exactly.
Displacement by acceleration.
Yeah, as long as
Suppose
you're
what change
intuitive,
scale?
as long as you're intuitive about these ideas, like whenever they give you a problem, like uh, we had this problem, the time period was 2 pi root over m by k. We had this problem, the time period of 2 pi root over m by k. We had this problem, the time period was 2 pi root over m by k. They simply try to twist the question by saying, giving a pulley and connecting the spring block system like this and ask you the time period. It shouldn't be a big deal because
Like forces won't change scale.
yeah, nothing is really changing. So the time period is clearly 2 pi root over m by k. Nothing really changed. Look at this question. Did anything change here?
So here pulley is massless or having mass?
Every pulley is massless.
Okay, here
Okay,
because
we can't
have
take
the
the mass of the
measurement.
pulley. That will again bring us the angular SHM, which will be a tomorrow's topic. So we don't discuss that today. Look at this problem. Is anything changing here? This is an interesting one. Aniket.
Uh,
No, sir, it's still the
no,
same.
no, sir.
No, you are stupid. I would say you are stupid, Aniket. Why? Ganesh has
Because there is
something to
tension
say.
acting on the block shell. There is
The
the tension
displacement
forces are
is
acting on the block.
Displacement is
changing, right, sir?
okay. I thought you almost had it, then you lost it. Displacement is
Sir,
what?
sir, like block will come by X,
Mm-hmm.
spring will extend by
Spring will
2x,
extend by also
2x.
x.
X by 2, X by 2.
2x, sir.
2X,
X
sir.
by
Okay, let me discuss these questions. Watch this thing. Okay, if in this first case, if the block moves down by x, the restoring force was kx only. If it is moved by x, the restoring force was kx only. If this moved down by x, the restoring force was kx only. It didn't change. In this case, if it moves down by x, the spring force that is created all the way here is kx only. Even though in this case, guys, remember it's not the direct spring force, it is a tension which is also equal to kx, which is acting on the block as a restoring force. So the restoring force was kx only, it didn't change. Not big of a deal. But look at the fifth problem. This is an interesting one. If I pull the block by down by a displacement x, the pulley has to come down by x, which means there will be an x here and there will be an x here. Both the x's will be taken from the spring only. So the spring is actually expanded by 2x. Now the problem is not over yet. Watch it. When I move the block by x, there was a 2kx tension here that is created. Now, if there is 2kx, this is also 2kx, which means this tension will become 4kx. So 4kx is a restoring force. So whenever I write the restoring force, you didn't understand what just happened, please ask again. Okay. The restoring force this time is 4kx, not just kx. I moved it by x and it gave me 4kx restoring force. So restoring force equal to 4kx, ma equals to minus 4kx, acceleration equals to minus 4k by m into x. So the time period will be 2 pi root of m by 4k this time. Interesting.
Yes, sir.
Let me give you another
Yes,
problem
sir.
then. Uh, look at this one. Try to displace the block by a small displacement x. If this comes down x, this expands by x by 2. Get it or not?
Yes, sir. Then the same process.
Exactly. So the force in the spring will be kx by 2. If this is kx by 2, this has to be kx by 4, kx by 4. So if I move it by x, the restoring force is kx by 4. So I'm writing, this part is a bit confusing for people. Take some time to absorb what just happened and write minus
Sir, I
kx
didn't
by
get the
4,
kx.
ma equals to minus k by 4 x, a equals to minus k by 4 mx. The time period simply will be 2 pi root over 4m by k.
Sir, I
Take
didn't get
this,
the x by 2 part, sir.
what?
Sir, I didn't get the x by 2 part.
Yeah. If the spring expands by x by 2, the pulley goes down by x by 2. Agree?
Yes,
If the
sir.
pulley goes down by x by 2, there will be x by 2 here and there will be x by 2 that is gone. Like initially the string was here, now it is here. So the string will move by x. We
Okay,
used it
sir.
in,
Okay,
we
sir.
used
Got
it
it.
in reverse ideas. Like if it is moving by x, the spring has to expand by x by 2. Get it? No?
Got it, sir.
Yeah. So just look at these two problems for today. There are a lot more complicated. Like I will give you a problem saying, uh, in an advanced level problem, I can give you a problem. If somebody is interested to do it, try to do this problem. Try find the time period of this thing. You will probably kill yourself doing the problem. No, this is not that big of a deal. There are more problems like this problem, right? By looking at it, I can give the answer saying 2 pi root or m by k, 2k, 3k, 18k. So sorry, 16k, I guess.
16.
Am I right? Not even 16, 64, I guess. You'll get 64k. Okay, I'm not really sure about this problem. I think it is 64k because you'll get x.
Yes, sir. It is 64, sir.
You'll simply get it multiplied twice. So
Yes, sir.
twice, and then twice. So you'll get m by 64k. As far as I remember, I could be wrong also. And when there are two springs involved, the problem gets a little weird. We will talk about these kind of problems in tomorrow's class. Like when
Sir,
there
I
are
got that answer. Previous one.
this one.
Yes, sir.
Okay, good.
Can I say once? Like you said this right now.
Are you saying my answer is wrong?
No, that other answer. Can I say my answer?
No, you actually got a different answer or what?
No, for the previous one, for the side one, what you gave us, the homework type of, where the block is downward
Sir, the
and that
double
springs
spring.
are up.
The
The
double
very
spring
first
one, this one,
double spring one. Sir.
double spring one, you
Yes,
can't
sir.
even try right
Yes, sir.
now. No, I'm pretty sure you can't do it. There are constraint relations involved in this thing. You can't do this for sure. I'm pretty sure about it. We will discuss that in
Like
a
our
separate
figure,
session,
sir.
not in a class. Okay.
Okay, sir.
Let's end this today's session. So all these kind of models, all these kind of ideas, just take them, grab them, and try to understand them, absorb them. Watch this class again if you really want it. And I want you people to try all these questions. leave the questions in this page. Maybe we can discuss them, the questions that you're looking at this page, we can discuss them tomorrow, but all these questions must be tried. The previous page must be completed by now. Leave this page out and try to complete this page. All right, guys. So tomorrow we'll be discussing more complex and more ideas, and then I'll discuss anger, SHM, and by day after tomorrow we will end this topic. Alrighty, guys. Alrighty. So I'll be clear about it. Just stay in the class for a second. I want to end the recording. Bye bye.